Ready to start. Thank you. Chapter 3 is all about applications. Go anyhow. Hello. Well, we'll see if this recording works or not. We start with sort of physicsy stuff. Sciences, chemistry, biology. Then we'll do what are called and then we'll look at related rates, which is if we know how fast that changes, and that's where it gets fun with implicit differentiation. Yet again, but in general, what you'll find in this chapter, Raman, who's listening, is that it's relatively easy. Nowhere near as complex as we Gradient equations, not so much, but then what does it mean? That'll be more the challenge later on. To begin with, it'll be not bad at all. So you all know S means position, and delta S is displacement. Okay, and average velocity would be delta S. Displacement over delta T, which is a bunch of animals. Okay. And velocity. Well, yeah, that's because you don't know any better yet. It's because, yeah. Derivative. No, I think not. Okay. Derivative of time function is going to be velocity. It's the absolute value of that. So, with the speed? No. S is absolute value of V, I tell ya. That would just be so using the letter D for anything else. Average acceleration, change in velocity over change in time, instant, or the second derivative of position with respect to time. There we go. We have an example. (122 meters high). 122.5 meters. That's really high. Come on. Its height after t seconds is given by this function. So to make you happy, there's no s. We use h, I mean, for height instead. We want to figure out the velocity of the ground. So what do we do? Children. What's the derivative of height with respect to time? Okay. So is that my answer? velocity when it hits the ground. So what do I do? Okay. So oh, well, pause for a second here. So you're used to saying, in this case, it always. There are situations where you could where it would make sense. Keep the positive 5. Question? Stay tuned. Okay. So we just plug in the 5 about units. I don't care because that's not my answer. Yeah, well, it's a little bit different there because here we weren't even given units for what is this 9.8. What are the units from that? Right? If I'm just plugging in time, it looks like I'm just plugging in seconds. Is this negative 49 seconds? So, and if you think this was a height, and so what is the derivative? It's a what? It's the change in height with respect to time. Shh. Please stop talking. So it's going to be meters per second is what the derivative would be. So we'll just stick it in here because we didn't have those units when we take the derivative. We're doing the rate of change in height with respect to time. So typically what we'll do is we'll save the units just to the end of the question through where the units came from. So what does this mean? Meters. In 1 second, it traveled that far, which is pretty fast. Thing that was it would do some damage at that point if it's get into the damage. There we go. Was there a question? No. Okay. Check it. Any questions with number 2? Easy enough? All right. And many of you have gone to time on that. I would have to know more information. Like mathematically, sure, we can multiply functions together, but in terms of a situation, it depends on the situation.
You know how you wrote triangles for a if you give us a question on a test where it's not S, and what is the answer to that question? Like, what is the kind of S?
Potentially, but I won't. We'll do some other complex things instead. At 2 seconds, what's our position? So then we're ready to sketch our graph. So now I do know that, and they're somewhere over here. Your scale does not have to be exact. In there, just So, are you ready with me? Watch this. This is what's happening. We have 1001, 1002, 1003, 1004, 1004. Oops. Whoa. I know that was crazy. And then 56 was over there. Ooh, there's a little jerk. So, what we'll do is now, just drawing that is semi-helpful. We have our positions here, but it's useful for us to put the times we were at those positions. Because 4 seconds, we're back at 8. So I know that when we stopped here, we actually turned around, we switched directions. Switch directions because we had to end up there. It can only switch directions when the velocity is 0, right? Because negative velocity through 0, so it has to have hit 0 when it's going to change directions. That's
Let's see. Draw the graph. Which point on the graph does hard case white?
we will always ask you to draw the graph first, and then we'll ask you about it. As in these questions, what's our displacement? What do we do? Displacement. What do we do? Not quite. Displacement is just final minus initial, right? So we're question. Hey, Jazz. You look a little more excited than everybody else in the room. Or, the math is just, yeah. All right, distance. What do we do? Total distance it travels. Yeah, so like this, kind of relations, but especially if we have the diagram. So if I go from -8 to 12, that's how much? 20. And then I'm going to go from 12 to 8, that's how much? So I'm at 24 so far. And I'm going to go 8 to 28, 44. Distance. Just for those of us. We're good. When is acceleration? We're going to do a derivative to answer. Just think through. So for this direction, from to 12, acceleration. Had some velocity and then it stopped. The acceleration had to be in the opposite direction to make it slow down and stop. And then it started moving in the. Once it starts moving to the left, what direction is acceleration? It's still to the left because it's speeding it up in this direction. So it's up, it'll because the acceleration is always down. So acceleration is left, 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 but then something happens because it slows down and stops again. So it must have switched directions to slow it down and then speed it up in the pond. The velocity function would look like a the Raman. Acceleration is 0. That's where it's going to switch from the negative direction to the positive direction. So we velocity. So that'll be 6t minus 6. Where is that? Which is in between that 2 and 4 seconds. We can't always assume that it's going to be halfway in between, but in this case, it was halfway in between those two. Velocity when acceleration is 0. Plug in 3 into the first derivative. So we want we have 3 plus 24. And what? It makes sense? Because our object is moving to the left at that point. Yep. Nope. So you are ready to try one. Check your. Your attention, please. I'm going to run through the rest of this page. Getting the graph, are we all good with that? Okay. So, then finding the total distance, you just add up all the little distances, you get 90 meters. Good. When is the acceleration equal to 0? Find the acceleration function. When it comes to sketching the graph, few people have asked, and what I would do is start with the line, because that's easy, and then you can do the quadratic gives you important information about the you would end up with. Okay, to begin with, just look at the line. The x-intercept is the vertex of the quadratic, right? Because if my acceleration is 0, that means that my tangent line was horizontal for my, and where my velocity function has zeros, those will be the maximum and minimum points on my cube. A whole new world. This is 1, 2, 3, 4. Vertically, we don't know what the scale would be, and it would have to be different for each graph. What the units are different vertically. There we go. Have a good day.